Welcome to everybody to the very first Decode Friday. Decode Friday is a meetup organized by both Drew, who are our hosts. So thank you to Drew for being our host, and Kings of Code. And the idea of Decode Friday is that we unwind after a week of hard coding and solving problems on the server and just listening to cool talks and being inspired to start work the next week. This is what's on for today. We're going to start with Ben, then we're going to have a small break to gather our thoughts, talk about what he's talked about and maybe ask some questions, and then we're going to have Sergey. And then after Sergey we're going to have a nice pizza. And that's it, that's all I have to say. I want to get into it straight away. I want to introduce you to Ben Noordhuis. And Ben, he works on the core of node.js, and he works also for Strongloop, who provides solutions for enterprise solutions for node.js to larger companies. Ben, take it away.
Sorry, but hey. Hey, my name is Ben. I work on node.js core. And, oh wait, before I start, how many people here know what Node.js is? Please raise your hand. So that's everyone. How many of you have actually worked with Node? That's not as much as I would have hoped. Because today is not really an introduction to Node.js, my first baby steps in Node. On the other hand, it's also not really into the deep end. If anything isn't clear or just doesn't make sense, please raise your hand. I don't mind interruptions. I don't mind interruptions. I don't want to lose half my audience. So.
Can I make a suggestion?
You can, and you will, I think.
You could do some really quick, like a rundown of the core. Weirdness of Node, in the sense that it's totally like single-threaded, and that it's that for that reason no I/O things can block, I/O
right.
operations can block, and therefore that you need to use callbacks everywhere.
Right.
Maybe good just to have like a base understanding.
Yeah, good suggestion. Okay, Node.js is server-side JavaScript. As mentioned, it's single-threaded, which means that you cannot do blocking operations because every blocking operation would block your entire process. If you want to do high concurrency, which means a lot of active clients, that of course is not an option because the first time you would block all the other clients. So Node.js uses event-driven asynchronous I/O. What that means essentially is that you don't block, and what's more, you tell Node, hey, I have this TCP socket and I would like you to notify me whenever there is something of interest, when new data comes in, or when it's safe to write without blocking. And C programmers have been doing this for years. More like decennia. Python has Twisted, which has a similar approach. Ruby has Event Machine, which is also asynchronous, non-blocking I/O with a couple of caveats. Anyway, so event-driven asynchronous I/O in itself is nothing new, but what Node.js brings to the table is that it's JavaScript, which means you can use the same language on both the server and the client. Which, when I started out with Node, wasn't really what attracted me, but apparently it's the single most popular reason for switching to Node. Many people find it very attractive. Am I still making sense so far? Yeah. Okay, thank God. Okay, so Node is asynchronous, which means you need to use callbacks all over the place. The callback is a function that gets invoked whenever the event you're interested in happens. So, hey, node tells you, hey, there's data to read, calls your callback, and your callback has this data. Same for writing. Node tells you, hey, it's now safe to write again. The kernel send buffer is empty. You can write, and it won't block. It invokes your callback, and off you go. Okay, so callbacks. Callbacks are both loved and hated by users. And I think it's safe to say that it's only a minority that actually loves them. Most people have a kind of uneasy relationship with callbacks. There are several solutions. Promises, which is a kind of everyone here know? Is there anyone here who does not know what a promise is?
I wonder how many people do know, but that's just I don't think. Let's ask the question.
Okay, so normally your code is callback driven, which can lead to this kind of, it's called the Christmas tree, where you have deeper and deeper levels of callbacks. So what promises do, they turn it kind of inside out. It's too bad that I thought there would be more people experienced with Node, because otherwise, else I would have prepared a couple of examples. So, but I will try to do my best to explain what a promise is, if necessary, with making the necessary motions. Okay, so a promise is essentially a callback in disguise. What it does, you say to the environment you're running in, hey, do this thing, and then you go on to do whatever else you need to do, and when it's time, you call in on the promise, which means that this promise, it's probably just another callback. When you call it in, you either block until it's ready, or if it's already run to completion, you get the result immediately. This presumably makes dealing with event-driven code a little easier. I myself am not all that convinced. Newer versions of V8 support JavaScript Generators, which is another approach to circumventing callbacks. I'll not go into too much detail because I'm afraid I'll lose half the audience. Maybe.
What is the normal language that you use?
I'm using Javascript day in, day out, so to say. Or CoffeeScript most.
Alright. So basically what you do with promises is I'm executing a statement.
Yeah, I know promises very well. I've made my own promise implementation, so I just was wondering how many of the audience if they.
Okay. Have I already lost half the audience? No?
No!
Okay, I'll try harder. Okay, so callbacks, promises, generators, what have you. They're all ways of dealing with event-driven I/O. Another approach that is embedded in Node.js core itself is called streams, and it's really for moving data from, well, let's move on to the next slide because that's where I'm going to explain what streams are. Streams are very much like Unix pipes. Data comes in at one end, you either observe or modify the data and shove it out at the other end. And as an application, as a stream, as a pipe, you don't care what's at either end. You don't care where the data comes from, you don't care where it goes to, just that you can do your thing. And here's an example. So in your favorite shell, be it bash or ZSH, you would run this example to extract the first field of the input, sort it, remove duplicates and count them, and then sort them again, this time numerically. stack, by the way, that's reverse cat. That's a GNU Core utils thing. If you're running on a Mac, for example, or a BSD-like system, you won't have it, but you can use sort-min-r. Okay, so the equivalent in Node looks something like this. Process.stdin pipe yada 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 yada. What you're essentially saying is, hey, all data that comes in from standard input, pipe that to this class called cut, then pipe it to sort, and so on and so on. And eventually your data comes out at the other end, transformed to whatever you want to. So, the basic concepts for streams are that you have sources and sinks. You could also call them readers and writers. Data is ordered, which essentially means that it's a FIFO. Data that comes in first goes out first, unless, of course, the implementer of the stream decides to rearrange things. Same goes for reliable. Segments, data is not dropped unless, of course, the implementer makes it so. One important thing is that the streams implementation in Node uses a push rather than a pull model. And push means that the producer of data tells the consumer, hey, I've got more data for you, rather than the other way around, where the consumer says, hey, I'm now ready to receive more data, please give it to me. Both models have their merit. If you're going to ask why does Node use push rather than pull, there really is no reason. It just seemed like a good idea at the time. And one of the important things about streams, they handle back pressure. And back pressure is, imagine you have a network connection. Network connections are generally quite slow compared to, for example, reading from disk. You can read from disk at a rate of several tens of megabytes, if not more. You can usually only write at a rate of several hundred kilobytes to the network. Let me move on to the next slide, which ties into this. This is a basic message of the day service. If you run it and connect to it, it will print whatever your message of the day is. So what it does is it opens /etc/motd, then sends it to the socket. We create a server here, tell it to listen on port 8000. Okay, so disks are really fast in comparison to networks. You don't want the entire file to get buffered in memory. MOTD is usually quite small, but say you're sending out video data. You don't want to buffer hundreds of megabytes in memory for each client. So the way streams work in Node, data gets sent to the network. When Node detects that the kernel send buffer is full, what it does, it passes the file stream, which won't do anything, won't consume resources until that time when it's safe again to send data out of the network again. Then it will resume the file stream and start sending data again. This is probably not all too earth-shattering, I think, but same example, but this time for HTTP. It's almost identical, only you send it to the response object in this case, rather than the raw TCP socket. Here is, I made a joke. A chat service for narcissists. Okay, this demonstrates another aspect of Node.js streams and something you cannot do with Unix pipes. You can send the data from a stream back onto itself. It can loop onto itself. What it does, whenever a new connection comes in, it connects it to itself. So if you, as the example shows, if you connect, you type in something, you get whatever you typed in back. Still not too shocking, but yeah. The nice thing, of course, is you can do all this in just 3 lines or 4 lines of code. Okay, here is a slightly more advanced example. What it does, I can actually show it probably, provided, of course, this, well, never mind. So what happens here is that we start another TCP server. When the connection comes in, we connect it to a REPL. The REPL is a module in node.js. REPL, of course, stands for read, eval, print loop. That's exactly what it does. You connect, you have a JavaScript REPL, actually you have a full node.js console to your, at your disposal. Here I apparently executed the very interesting code 1 + 1 = 2, but you could, for example, from this REPL start another TCP server. It's just, yeah, it's a full-blown node.js server that you're talking to. And here is a yet more advanced example. This is an HTTP server. It lets you select the algorithm and the password and then accept and then encrypts data that comes in and sends it back to you. Usage example is here, done with curl. Data is prism.this, encrypt with AES 192 and use the password secret. All very trivial really, but I hope it does demonstrate the power of streams in Node. They're there to make simple things simpler and hard things, well, hopefully less hard. Okay. Who of you have worked with streams in Node.js 08? Yeah, Jan and Sergi. Okay. Should I go into excruciating detail what was wrong about the old streams implementation? No, okay. Right you are. So, the new stream implementation. The thing with the old, with the bad old days was that it was really easy for implementers to get it wrong, and a lot of people did, and it led to no end of confusion, worry, and just buggy applications. So what we have now is easy to use, however, it's not fully backwards compatible. But most of you probably won't care because you didn't use 08 anyway. Okay, so the new streams in 010 have several types. Readable, writable, duplex transformer. There's also a pass-through stream, which is about the most uninteresting stream you could imagine, because the only thing it does is, yeah, it copies data from A to B. Is this actually readable for you guys in the back? Yeah. Okay, okay. So, a short example of a readable stream. It reads in the dictionary and it generates, it produces as many words as you want in a random fashion. The thing about the new streams implementation is that it's easy to use. You only have to implement _read. This function receives a size argument, but it's fully optional. It's only when you're... No, just remember that it's optional. It only... It only matters when you have, on the one hand, a stream that produces lots and lots of data, and on the other hand, a really slow consumer. Yeah, optional. Your readable implementation does not emit data directly, it pushes it into a queue, which is then later on consumed by the data sink or the reader. So the next step of the pipe. And if you ever feel the need, you can unshift chunks, which means you put them at the front of the queue instead of the back of the queue. Okay, nothing too fancy. Writable. Actually, I tried very hard, but I couldn't come up with a really good example of a non-trivial writable. This one just splices, sends data that comes in to both standard out and standard error, which is a silly example because, like, you can just do process standard in pipe to standard out and standard R. And what's more, it's also wrong because it doesn't handle back pressure. Okay, same thing about writable. You only have to implement _write. You always get buffers. Okay, most of you haven't really used Node all that much, right? So, do I need to go into detail what buffers are? No. Yes, no. Okay, no.
You get the idea when you start explaining.
Yeah. So, yeah, well, that's writable. Duplex is even less interesting. It's just both readable and writable. A transformer. So transformers are kind of interesting. They are like, for example, unique-c in the Unix pipe example. They, on the one hand, consume data, do some kind of modification, some kind of transformation, hence the name transformer, and put it out again. This is the this is an implementation of a stream, a transformer that uppercases all its input. It's quite trivial, well, nothing too fancy. Like readable and like writable, you only have to implement a single method, _transform. You can also implement _flush if you want, and that's mostly for when you have some kind of protocol that has trailing data. For example, I maintain an iconv module. Iconv is for converting from one character set to another. So there are a couple of character sets that have this, it's called a shift sequence. It doesn't really matter what it is, but what it boils down to, after you've converted all the characters, it's possible that there are still 1 or 2 or maybe 3 bytes that need to be written out. That's when you would use the flush, or that's when you would implement the flush method. Node will call it when it knows that the stream is nearing its end, but just right before it actually dies.
Can I ask a question? Is it safe to always call flush at the end?
You don't have to, Node does it for you.
Right.
These methods are strictly for implementers. So if you're making your own transformer stream that does those iconv transformations, then you would implement _flush, because you may have these trailing shift sequences.
Okay.
So far, so good. Okay. This is how you would use it all together. Okay, not too exciting, but there's not enough room on these slides for a more full-fledged example. There you go. There's another thing, which in my opinion is kind of pointless, but so far these streams have all used either buffers or strings, mostly buffers. Buffers is the default, but you can use strings if you want to, even strings with encodings, UTF-8, ASCII. You can even have hex-encoded strings if that's your fancy. But there's another mode called object mode, and well, it does what it says. It lets you pass and modify objects rather than strings or buffers. Here is a quick example. Why do I think this is pointless? Well, you can achieve the same thing just with buffers or strings. But back when we were adding the new streams implementation, there were a couple of vocal people who were arguing for object mode, and for better or worse, there it is. Well, exactly that. Okay, so in conclusion, there are a couple of stream types: readable, writable, transformer, just what you would expect. They're easy to use, easy to implement, which is a great improvement on the 08 days. They're also mostly backwards compatible, but not fully. I think, Jan, you've experienced personally how awful those bugs can be, right? But hey, that's what he gets paid for. And there's no, I feel for you. I mean, my heart is bleeding for you, Jan. So there. So far, questions? Yes.
The difference between 8 and 10, when I'm trying to learn a new framework or language off, and I'll just Google stuff, and one of the most frustrating things is following a how-to that says this is how you do it, and it turns out I'm doing it the wrong way because it's changed since then.
Yep.
Is there, and like when was 10 developed, so I can at least say search for things that were made since this date?
Is the question, when was Node.js 010 developed, or?
When are we on? I guess how do I know what I'm looking at is how to for the right way and not the old way that will introduce bugs that will cause me pain?
Oh, right. So Node.js 010 is the current stable release.
Okay.
So if you're developing a new application, you would use 010, not 08, because.
I should be. If I'm following a how-to that was written a year ago, though, is it likely to give me the wrong way or the right way?
That's probably the wrong way.
Okay, so pretty recent how-tos then only.
Is
Yeah.
the module still named Streams 2, or?
No, well, that's the code name. Essentially, you just include require the stream module, and well, that's all you need.
But isn't the readable stream class name, is that not a new name? The class name readable stream. That's it.
Oh, right, yeah, so it's a new addition in 010. If you want your code to be compatible with both 08 and 010, there is a readable stream module on NPM. NPM is the package manager for Node, which, well, does what streams do in 010, but also works in 08. So,
It's compatibility.
yeah. One sec. Going back to your question, so it's true that the tutorials you'll find are often outdated, but this will become less of a problem over time because the core it's mostly stabilizing. We're not making any big sweeping changes anymore. Mostly.
I had a question. You skipped over the duplex, but I guess that's the last example that you showed where it had both the readable and the writable. That's a sort of example of duplex implementation.
Yep. Okay, how are we for time?
Oh, we're still good.
Okay, nice, because now we get to the fun part. Time permitting, and I propose nothing because it's completely unrelated to what we were just discussing. You're probably wondering what this is going to be about. Integer division. So, now we're off into the deep end. Okay, I assume everyone here knows and uses JavaScript, right? If there's anyone here who has no experience with JavaScript, please raise your hand and then proceed to leave the room. Okay, excellent. So V8 is the JavaScript engine in Chrome and in Node.js, of course. V8 is a JIT, a just-in-time compiler. It actually does no bytecode interpretation. It only generates machine code. It actually has two compilers. It has a baseline compiler that produces good enough code, and it has an optimizing compiler that produces hopefully optimized code. However, as you can see in this example, this, by the way, is an internal V8 function, and this as well. If you have a function that does the equivalent of math.floor x divided by 3, what it does, if you look at the generated machine code, it generates an IDIF instruction. IDIF, as we all know, is expensive. You don't want IDIF. A single IDIF instruction takes between 26 to 190 CPU cycles. It's usually about 50 to 80. To put that in perspective, most instructions only take 1 or 3 cycles. Actually, on newer Intel CPUs, there are a lot of instructions that only take half a cycle. So 190 cycles is, well, civilizations rise and fall in the time it takes to do a single IDIF instruction. So it's easily the most expensive instruction you will use in your regular code. That is, unless you're a kernel developer, but I assume most of you aren't. So, can we work around it? Well, of course. And this is where this nice one-liner comes in. We take the number, we multiply it by this magic constant, and then shift it to the right 16 bits, which is essentially divide by 65536, but you all know that, right? Right?
Yeah.
Okay, good. So, if you now take a look at the generated machine code, you see it does an imul followed by the shift, and that's a big improvement because usually mul and imul takes between 1 and 20 cycles. Actually, imul on modern machines usually only takes up to 5 cycles, so it's quite fast. Oh, and another funny thing, imul is signed multiplication. You would expect that to be slower compared to the mul instruction, because mul is unsigned. Should be easier to implement in hardware, in digital gates. However, imul is usually almost always fast, and that's probably because it's the most used type of multiplication. So AMD and Intel are probably optimizing for it. Okay. So the great thing of this example is that it works for both signed and unsigned division. As you can see here, it gives the correct result for -100, which is what you want. There are, by the way, algorithms which only work for numbers larger or equal to 0, which are a bit faster still, but don't work for negative numbers, so I won't consider them here. Problem is, it doesn't work for large numbers, and you'll wonder why that is. Okay, so the thing with JavaScript numbers is, I think I have that covered on the next slide. Yeah, probably. Okay, large numbers don't work because JavaScript numbers they're not integers, they're floating point numbers. And doing binary or logical operation on them, like for example a logical AND, only works up to 32 bits. But what's more, that's 32 bits of sign precision, so it's not over 4 billion, it's only from -2 billion to +2 billion, which is, of course, those are still big numbers, but they're pretty limited. And it also means that you can't just multiply numbers however you fancy, because you'll soon, especially when you're multiplying by hex 5556, which is about 200 something, well, you'll soon go over the 32 bits range. And to add further insult, if you use a larger magic constant, you actually reduce the range for which it works. So that, of course, sucks. Can we do better?
Sure.
Yes.
Of course. Well, this is very self-explanatory, right? So, what does this do, I hear you think? This actually exploits the fact that the reciprocal of 3 has a certain pattern, a bit pattern in memory, which we can quite accurately approximate with just shifts and adds and one subtraction. So this is fast. Discounting V8 overhead, you're only looking at 20 cycles. And it also works for signed and unsigned division. And what's more, it works for, well, quite large numbers. Of course, we can use the same approach for other divisors, for example, div10. Well, it's mostly the same, only, of course, a divisor of 10 has a slightly different reciprocal. You need to use a different sequence of shifts to approximate it, but the basic principle is the same. Which brings me to my conclusion. Division is expensive, there's no way around it. But the good thing is you can always reduce it to elementary operations. Adds and subtractions and shifts are, well, they're about the most basic things. For example, the 6502, that's the CPU that was in the Commodore 64 and the Nintendo and VIC-20 and the Apple II. It doesn't have multiplication or division instructions, but it does have shift and add and subtraction. And, well, we can do fast division for a big range of numbers. Questions?
Why doesn't the V8 optimizer does this?
Oh, right. So that brings me to my, I should have put that in the slide. I have a couple of patches for V8 for lithium, that's the optimizer. Oh, that's another fun fact about V8, if you will allow me a minor digression. So V8 has these two compilers, the baseline and the optimizing, and the baseline is called hydrogen, which is the lighter element, and the optimizing compiler is called lithium. Can you tell there's a couple of physics geeks on the V8 team?
What are all the elements in between?
I don't know. It's possible they wrote like... Maybe they've written like, what is it, 10, 16 compilers in between? Okay, so why does V8 not do this? Should I give the political answer or the... Oh. Okay, presumably they just haven't gotten around to it, or they didn't think it was a worthwhile optimization. However, I'm working on this Nintendo emulator in JavaScript, which uses division by 3 a whole lot for some reason. So that's why I discovered that it's so slow. So I have a couple of patches pending that add optimized division for a couple of concepts like 3 and 10 and 23 for some reason. So there you have it.
So how do you comment these low-level facts?
Sorry, what?
How do you comment these low-level facts that the divisions are extremely slow?
How do I comment?
How do you come to it?
Oh, how did I discover that, or how do I measure it?
Discover it.
Okay, so yeah, this Nintendo emulator, which is what I actually was going to do the talk about, but I didn't get around to finishing it. Okay, so the original Nintendo has 64K of memory, I could of course just allocate a buffer or an array buffer that's 64K. But I thought, hey, we can do better. V8 has this optimized way of storing integers. So I thought if I take a slightly more advanced approach, I can store like 30 bits in a single integer. And that would save me, instead of 64K, I would need only 28K. Hey.
You all got those mnemonic codes.
Yeah.
And how did you come with that code? With soft I, for example?
Oh, right. No, so, yeah, right. So V8 has a built-in disassembler. At least if you build V8 in debug mode, it can dump.
Give mnemonic code.
Yeah.
Okay. Cool.
Which is what I look at all day long. Yeah, that's my life. Mama was right. I should have become a lawyer, but hey, here I am. Yeah.
So to put this overhead in perspective and also look at maybe other approaches to like address this problem you discovered, what would happen if you like instead of somewhere say divide by 3 or so, put a function in, a function call which is called div3 or so, and put in the 2 arguments, or no, 1 argument, the argument you want to be divided. How much overhead does such a function call impose in terms of instructions?
0, because the optimizing compiler in V8 is very inline happy, which means if you have inlining is where you take the body of a function and instead of generating a call to said function, you just inline the body in the caller. Function calls are relatively expensive on x86, also on ARM. So of all the optimizations, inlining is probably the biggest win you can make. And everyone who implements their own language, well, inlining is the first thing you implement in your compiler because, hey.
Yeah, so as you said, the function call basically is gone, so the overhead is gone.
Of the function call, right, yeah.
So then I wonder, instead of like putting all these optimizations in the V8 compiler, maybe there are kind of rules to there's probably kind of logic behind what kind of bit shift operations or whatever magic you should do to get a very fast division or an integer division,
right,
or a 3 or whatever number. So couldn't you write like a code generation library which creates well, effectively an anonymous function which you can put in?
Right, so V8
and
is
all like in userland, and Node is all about userland, right?
Right, right. So V8 more or less does what you describe, only currently it's not smart enough to recognize that some kind of division can be optimized.
Yeah, but what if you do it manually? You could write a library which could generate functions which divide by any number you want, which just...
That's true, but why would I do that when I can just do it at the root in V8 itself?
Oh, well, because I think, well, that's at least what Isaac Sluder is kind of proclaiming or advocating for. Do as much in userland and keep core small. But that applies to Node.js, and I'm just trying to follow this balance between putting things in core, well, you could just use...
Yeah, but this is not putting things in core, this is putting things in V8.
Oh, yeah.
And the upside is it benefits everyone who uses V8, not just Node. So if we fix this in V8 itself, Chrome also benefits.
But if you do it in an npm module, then you would also have the speedups in Firefox and IE10 and whatever.
There's no operator overloading, so then you have to write all your code like...
I'm not saying operator overloading, I'm saying putting in manually a function call instead of the division thing. And I wondered about overhead.
I think this is a very interesting discussion.
But we're
What I
going
want
over
to do
time.
is thank Ben very much for his talk.